Hi everyone, welcome back. We would be starting with our next session, and we'll have Dan and Pedro talk about uh, VM class secure and using Hyperlight Nanvix. So over to you guys.
All right, welcome everyone to our talk. We have VM class secure, Millisecond-Fast, cloud-native apps with Hyperlight Nanvix. A quick intro about who we are. I'm Danilo, or Dan. I'm a software engineer at Microsoft and a core maintainer of the Hyperlight project. It's one of the projects we're talking about today. I'm also the author of a book called Server-Side WebAssembly, which is soon going for print, just in December. So I have a couple of codes to give away, by the way, at the end of the talk, for maybe some questions or something like that, for free books that will get shipped to you once they get printed. And I'm here with my colleague, Pedro.
Hello, I'm Pedro. I'm a research software engineer at Microsoft Research. I have a PhD in operating systems and the creator of Nanvix. Yeah, I am happy for having you here and listening for us. Yeah.
Cool. So this is our agenda for today. Main idea is that we'll present you with a problem, the serverless trilemma. We'll then present you with our proposed solution, Hyperlight Nanvix. Then we'll go into a deep dive into security, performance, and compatibility. With the demo gods allowing, we'll have a live demo. And then finish off with some getting involved links and whatnot. Okay, so this is the problem that we have today. Serverless trilemma. Oftentimes, with a lot of state-of-the-art solutions that we have today in serverless, you have to pick one of these, well, two of these three things. You either pick fast cold start, you either pick strong security isolation, or you pick runtime compatibility, running your apps as they are. A couple of examples we have here. Starting off, we have containers. They're fast-ish, they're compatible. You can run essentially whatever with containers. However, the host system is shared. You have a big attack surface with containers. That's primarily because they rely on kernel features to provide that isolation, so cgroups, namespaces, right? And just between, I think, 2022 and 2024, there were 7 container breakout vulnerabilities reported. So they're not suited for multi-tenant isolation or something like that because it's very easy to break out of them. Then we have VMs. They're on the other side of the spectrum. They have strong isolation. They're very secure and they're compatible. You know, usually people associate VM with you put a whole Linux distribution in them and run, so you can run whatever. But that comes at the cost of very slow cold starts, between 100 and 300 milliseconds or more. Then we have WebAssembly, sort of the new kid on the block for server side. I'm obviously biased, you know, writing a book, but there's cons. One of them is, you know, WebAssembly is fast, it's secure, and even though you can compile from multiple languages to it, it will require recompilation, and that porting process is not always trivial. That's where we have Hyperlight, which is what I'm a core maintainer of. It's a CNCF sandboxing project. It is a lightweight VMM, or virtual machine manager, also known as hypervisors. A couple of key aspects there is that it allows you to create these micro-VMs that don't have an operating system whatsoever. It only provides you with some memory and a vCPU to run functions. So just compute or stuff like that. And it provides very strong isolation via, being VMM with backend like KVM or Hyper-V. So something that's been battle tested for a long time and is a very strongly trusted isolation primitive. Now, being a micro-VM with no OS and only memory and CPU, what we get out of that is that we have very quick VM creation time. That's between 1 to 2 milliseconds. Asterisk there is that we're not timing the process creation, which usually in systems turns out to be around 5 milliseconds, but that's what we get in creation time, which is really good. You know, faster, 100 times faster than your conventional VMs. And we have very light memory footprint with what you get out of the box from a default heap and stack that we provide. You have 192 kilobytes of weight. And if you haven't tried Hyperlight and would like to try it out, here's a QR code that you can scan. We have great getting started, and if you want to contribute, we have lots of good first issues and so forth. So I told you what Hyperlight is, but let's go a little bit deeper into how it works. Because we don't have an OS, so we don't have syscalls, so how do we get anything done? That works via what we call the host-controlled communication mechanism. So on one side, we have the host process. That's the process that's creating those VMs. When you create a VM, you can specify some configuration. That can be how big your stack is, how big your heap is, stuff like that. And once you have that done, you can then register host function calls. So these host function calls, they kind of serve as syscalls in the sense that it's stuff that your guest can call for specific functionality that it doesn't have inside of the VM, being as constrained as it is. And that's that Hyperlight host API that you see there. And then also on the other side, we have the micro virtual machine that the host can call to execute guest function calls. Those will be those functions, that's sort of the granularity that we operate at to do some compute. The guest can then, of course, exit with those host calls. And that's more or less how it works via shared memory boundary in the middle where we can serialize some components, like maybe parameters to a function and maybe the return from the guest. Okay, so that's how it works. But as you saw, we have a Hyperlight guest API, and to build these applications, they're specifically built with that API, and they're compiled to run on Hyperlight. So they're purposefully built applications to run very quickly. What that gives you is that quick startup time and low memory overhead, but because we have no OS, it's very hard to port your normal existing applications, and so this specialized guest code is required. And to answer that, we have...
So basically what we have, we just said, well, if you haven't tried for Hyperlight, by the way, you should. There are even like blog posts that we wrote in Microsoft for that. It's a very cool feature, but there is like, we struggle of like having more more fully featured applications to run on top of Hyperlight. And well, our answer for that is for sure introduce an OS, right? We just said, well, we should take out the OS. Now we are reintroducing it, right? But the idea here is that Nanvix is a completely from scratch OS that we are designing inside Microsoft, and it's an OS specifically tailored for cloud native applications. So basically, Nanvix is a microkernel OS written in Rust. Here's the source code. You should also like go check it out. But what's interesting is that we completely co-designed the OS with Hyperlight, which has this very, very lean virtual machine model, right? And the idea here is that we are doing this tightly integration so that we can deliver like minimal overheads and the maximum performance. And it's completely like designed for the cloud because cloud workloads are mostly like very ephemeral. They run for a very short amounts of periods, and we are just tailoring all the OS services for that. And Nanvix does bring all this compatibility to the table that is over 150 system calls, and it supports like POSIX, JavaScript, WebAssembly, and so on. So basically, Nanvix is kind of an OS, a very lightweight OS that you can run with Hyperlight and bring more interesting applications to this scenario. And here's the logo for Nanvix, and it's a dog, but it's mostly here to give you more time to go and check the QR code here for the project. Okay, so how we enable this compatibility, but still having this huge performance and density that Hyperlight can give us, right? So from the architectural perspective, Hyperlight, here you have your Hyperlight VM application deployed on top of your favorite hypervisor, probably Hyper-V, right? And what you have is on host side, you have this host process that offers you this Hyperlight host API that the application can leverage and do more interesting stuff, right? For instance, expose like specific applications that let you access an external resource. But then you can think about, okay, how we want to introduce an OS for that, right? I think that the immediate idea would be, okay, below my application, I put my OS that runs on the Hyperlight, right? And what does that mean, right? So imagine that you have an application that is written in Python, right? So it means that you first need to support a language runtime that it's a Python runtime. And believe me, you don't want to go there and write your own CPython distribution by yourself. That's another job for maybe 20 engineers to do, right? But then if you want to bring CPython or your Dino runtime to the play, you somehow need to support POSIX, because that's how life works, right? Okay, so if you are exposing POSIX to your application, then how you do that, right? Then Nanvix kernel can do a bunch of stuff, so it can provide you kind of like thread management, memory management, all locally inside of your Hyperlight virtual machine. And with that, you can do way more that you could do with Hyperlight vanilla. But still, maybe you want access to external resources, such as, I don't know, a file system, an Azure Blob Storage, or something like that. And, well, basically what we do, we kind of leverage this host process that has this Hyperlight host API to actually have a module there that is taking all the system calls that you have, the I/O system calls, do some filtering and routing from them, and basically the idea is that in your Hyperlight VM, you are offloading all those system calls to your host process, right? So by doing so, we can expand basically the capabilities of Hyperlight to all those 150 system calls. But then you can imagine, wait for a moment, right? Now I'm basically offloading some I/O system calls to your host OS, which can impose a threat, right? And that breaks the trilemma. Well, actually, this is the simplest deployment model, and this is just for educational purposes, right? So the idea here is more to go into more other deployment flavors that we can have with such a flexible architecture that really can get you all the security benefits, still maintaining the performance and the density. So the very first one, let's explore it. So imagine that you have there your Hyperlight VM. You are deploying that in your hypervisor. You have an host OS that somehow has this Hyperlight VMM process that is managing the VMM. But instead of having that system component that is handling all the system call offloading, instead of having that in the same process that you would have in the previous, as I showed in the previous slide, you basically deploy that as a sibling process running in your host OS. Well, if, for instance, you can consider that other process as part of your trust compute based, and you can even imagine that in most of cloud native deployment scenarios, we do that when we are doing TCP proxying or any kind of proxying to access external resources. You can do one step further and jail all these two processes running on your host OS in a container group, apply syscom filtering and so on to really restrict the access to the underlying host OS resources. Well, this is the multi-process architecture. It has two processes running on the host. One is the Hyperlight VMM process, and the other one is the system process. The thing is here is that the Hyperlight VMM is managing the Hyperlight VM, whereas the system process is handling all the I/O. You still are sharing the underlying host OS, but now you reduce the blast radius, because if the application is buggy, it's just bringing down the VMM process side of things. And you can still apply some caching mechanisms in the system process so you can have a very fast startup. But yeah, we are still sharing the host OS kernel. And well, in Microsoft, we are very careful about that. So what we do is having a very more elaborated deployment. So in this very elaborated deployment, you still have your Hyperlight VM running on top of your hypervisor. You have the VMM process, but then we introduce another VM. And that another VM is basically hosting that system process. Right now, what we actually have is what we are calling the disaggregated architecture. Because then you have like just 2 processes running on the host, but those 2 processes are basically managing the VMMs, right? And actually, all the code is hypervisor isolated. So the host OS is not shared at all, and you can then apply snapshotting on your system VM and enjoy all the benefits of that technique. Notice here that the system VM is now, the state that belongs to the application is completely decoupled from the state that is generic for whatever workload that you want to run. But, well, maybe you are not trusting me that can save you time and provide you like good code starts, so let's dive into that. Right now, we will check some performance benchmarks that we have for an HTTP server, Echo server application. And let's first understand what happens when you don't know your workload. So you don't know your workload, meaning that you cannot leverage snapshotting at all, for instance, in Firecracker, right? Because you don't know workload, how you will snapshot something that you don't even receive through the network, right? And by doing so, and here we are comparing with a bunch of other like solutions out there that are state of the practice, right? So when we do a comparison with Firecracker, and notice that this is a log scale graph. So we are boosting like the cold start latency over Firecracker by 10x, just because I can snapshot my system VM and restore my VM, my system VM from that snapshot. And for the very lightweight Hyperlight VMs, I can spin them up on demand. Okay, let's move to the situation where we can leverage Firecracker snapshot, right? Sure, when we do that, what we can do is just, we keep the system VM alive, because basically we can have the system VM running for a given tenant, and that's it. We just pay the cost. Actually, we do that for TCP proxying anyways, right? So when we do that, we are not even paying the cost for restoring the system VM snapshot, and we are just like spinning up Hyperlight VMs that are more capable. And again, in that scenario, we can provide a 10x improvement over Firecracker. And interesting enough, if you compare like Hyperlight Nanvix with like vanilla Hyperlight, or even process, say that you are spinning like a process in Linux, right? We are very close to that and giving you this like virtualization isolation for your application. So basically, Hyperlight Nanvix does offer these like additional benefits, right? Now let's take a look on the memory efficiency side of things, right? So memory efficiency and how many of these VMs you can pack is really important from the cloud provider's perspective. So still, when we compare a bunch of like solutions, we put like Hyperlight and process as the reference as well. But you can see that there is a 10x improvement over the number of VMs that you can pack in a given like gigabyte of memory. So in 1 gigabyte of memory, we can provide almost like over 200 Hyperlight Nanvix VMs that enables you to deploy more interesting things.
Yeah, so if you're looking at all this and you're thinking, wow, that's so cool, where can I use it? These are a couple of applications that we thought of highlighting. The first one, from my right, your left, is next generation function as a service. The new paradigm here is because these VMs spin up very, very fast, you don't necessarily have to keep a warm pool of resources. You can then just, end that VM and then bring another one back up, and it's just fast like that. The other side is Edge and IoT. In Edge, we usually run with devices that are very, very constrained, and because we spin up so fast and because our memory overhead is so low, we can pack these into Edge and IoT devices very, very easily. And the third one is embedded secure execution. Say you have an application, you want to run some third-party untrusted code, you can use Hyperlight Nanvix as a library to run that code in your code base. So now we'll go for the live demo section of this talk. It's a pretty long demo because we want to display a couple of things. The the first thing that we want to display is running various types of workloads. And for this demo specifically, we prepared C example, C++, JavaScript, and Python. And then we'll move on to displaying a demo that has access to the host file system. So there's some file system operations to show how you can then restrict that with Nanvix's mechanism of syscall interposition or interception. And then we'll put that all together with a cool demo showing how we can run AI-generated code inside of Hyperlight Nanvix. Okay. So let me bring up my terminal. Okay, try to make this very big, so hopefully it's seeable all the way in the back. This is the Hyperlight Nanvix repo. We have QR codes for that at the end, so you'll get to access it soon. But essentially what we have in this repo is a couple of things. One is we have the library for Hyperlight Nanvix that you can embed into your application. And two, we also have a binary, Hyperlight Nanvix, that you can run to run these from the CLI. Then we have a couple of guest examples. We have JavaScript, a file one, C, C++, and Python. And then the full-fledged example, and this is called interception. So let's walk through it. Thanks, Peter. I don't know if people can still, oh, thanks, appreciate that. All right, so what I'll show you here first thing that you'll want to do if you are in the Hyperlight Nanvix repo is that you'll want, or using the CLI, is you'll want to set up Nanvix's registry. So that is what downloads all the binaries that we have precompiled for Nanvix to run some of your workloads, like Python or Python to run Python workloads, Python 3, and QuickJS, which is a QuickJS engine to run your JavaScript workloads, together with the kernel and other binaries like that. So I'll do cargo run. If you're with the CLI, you would just run Hyperlight Nanvix, and I'll pass in the CLI argument to set up registry. I already have it set up on my machine, so this step is very, very fast. Doesn't really have the time to download anything over the network, but you see it's already cached over here. The next step that it recommends you to do if you want to run applications like C, C++, maybe Rust, is to pull the Nanvix toolchain. This is just a Docker image that contains Nanvix's GCC, G++, Clang, Cargo, and so forth. I'll do that too. I also have this already because if I didn't, that would be the end of the talk because it is a 15 gigabyte image, so it's pretty big, and that will take a while, I think, over this network. But luckily, I've prepared. And then with that, it gives you how to compile the examples that you have just in your local machine with that Docker image. So to start, we have this hello C example. It's very simple. It just has a main function, does some prints, some arithmetic, a function loop, and it returns. So I'll compile that, copying this command. And so you'll see here what we're doing is, if I can highlight the specific bit, is that we're calling GCC and passing in our hello C that you're seeing, compiling into this hello C. I already have it precompiled, so you won't see it show up, but no file or directory because I'm in the wrong folder. That's how you see it's real. And there we go. Now it compiled, and that's how that one would show up. I can also run the other command to show you how we would compile C++, but it's exactly the same thing. And that's how we would get that hello C++. And this hello C++ is also very similar with some includes for vector, string, so forth. But if you're not compiling something, you can just run it out of the box. That's the example for JavaScript. Same example as the hello C, prints, arithmetic, and the hello Python, hello Py, which imports JSON and does some operations like that. So let's actually run these workloads. I'll do a cargo run. Let me go back once. I'll do a cargo run. Yeah, I'll call guess examples, and I'll pass in the hello C. There we go. That's the execution. So running C in Nanvix. I can then run C++. There we go. C++ in Nanvix. I can then run JavaScript. And that's not what I called it. It's .js. And there we go. JavaScript. And now Python. One cool thing about Python is that before, so we had support for JavaScript and Wasm as well, actually, just through normal embeddings. But Python is something that we didn't have. So this is now all new from embedding Nanvix instead of Hyperlight. And there you see, that's what ran. With that done, I will also run our example for file operations. This file operations, just to show you really quick, it uses some QuickJS modules like standard library and OS to create a file, write to that file, then read the file, and get some file stats. So just running it like that with allow all. I see that we have all the file contents, checking file stats, so forth. Now let's move on to that syscall interception example. In this example, we are embedding Hyperlight Nanvix as a library, and with so, we're creating the syscall table, and we're using the syscall action forward to intercept that open@ system call that the guest is making and change it. In this example, we're changing it by just adding a log or eprint line saying intercepted open@, and then in the end, either success or failed. But really, we're just redirecting it to the normal libc other than that. So if I run that, this will be the same demo as we just saw, but you should see those extra logs. So let me do a cargo run example. And here we go. So you see those eprint lines that we added, those intercepted and successes and so forth. Now, another thing that I can do, this is live coding right here, is I can remove the forward, and I can also block the syscall entirely. So I can then run cargo run again, quickly compile. We get a warning that we're not using the logging function, but you see the demo ends right there. We could never open it, and so it just returns, and not owners, we're surfacing that we don't have access to that file descriptor. Okay, so with that, I showed you how to run all these workloads like C, C++, JavaScript, Python, how to intercept your syscalls and either block them or change their behavior. And I've showed you all that with sort of Rust hosts. If Rust's near your thing, that's fine. We also have a Node.js API, which is this one, allows you to do the same things. Create a sandbox, run a sandbox. And I'll show you that directly with Node. I will do Node examples, Node API. And this is just running the hello.js again, but now this time with Node. Now finally, to close off, let me go into examples. AI generated scripts. And in this example, what we're doing is we're using just OpenAI's API to generate some JavaScript code and then run it inside of the Nanvix sandbox. That's interesting because that's just LLM generated code, so it's untrusted, and it's something that we should potentially run in an isolated environment to protect the host. So instead of here, I will just do node main.js. By default, it will run 1. I'll pass in 5 to run 5 generated scripts. And here, what is outputting is all the scripts that are generated, some random stuff like multiplications and reverse strings. There is the output, generate pyramid. But the cool thing is that this is untrusted code that's been generated on the fly and is now running inside of a secure sandbox. Okay, now back here, just to close off. If you like what you saw and you want to get involved either by trying it or by contributing to it, this is the QR code where you can access it. This is the repo. We also host office hours bi-weekly via the CNCF. You can check out the agenda here every Wednesday at 9 a.m. Pacific. And we also we're on the CNCF Slack with the Hyperlight channel. And now, shameless plug, this is my book. We're going for print soon. I have 6 books to give out, so questions, you'll get a free book. If you don't have a question, you can still scan this code, and using the reject25 code, you get 45% off. All right, and that's it. Thank you. Any questions?
Yep, we have a couple of questions.
Since you are depending on a real fat virtual machine for this use case, how often do you have to eat the cold start of Hyper-V or KVM spinning up the virtual machine?
Did I get that one?
Just once per the tenant.
But if there's like ever an OS upgrade or anything that has to happen on that VM, would you have to then eat that cold start again?
Nope. Because you keep the VM running, that system VM is running for your tenant.
So it's once per VM restart, start or restart. So because you're running a full fat virtual machine, there's an operating system in that virtual machine, correct?
Yes.
So if that virtual machine operating system has to restart, you have to eat the reboot time of that.
Yeah, but that system VM is provisioned by the cloud operator. So we control when it restarts or not.
Okay.
Yeah.
Thank you, great talk.
Sure, thank you.
Hey, do you think you'll get to a point where you'll be able to not have to recompile applications?
So Nanvix is a different operating system. You cannot like take your Windows binary and make it run on Linux, right? And vice versa.
You do have similar like syscall interceptions like gvisor does, right?
Sure, but it's not Linux, so the ABI is completely different.
Okay, that's why the separate tool chain. Okay.
On the back.
So just to be clear though, the last one where you're running through the LLMs, so each time it iterated and it got back a script, you got a new VM to execute just that script and then it threw it away.
Yeah, that's right.
Okay.
So it was a new VM per request every single time that you saw. We just ended the VM and then ran a whole new one.
So were there any design consideration for choosing Nanvix as first, and do you have any like future roadmap for supporting other microkernels other than Nanvix in the future?
Yeah, we haven't, well, we don't have support right now for any other microkernels. One thing that we really liked with Nanvix, specifically for Hyperlight's use case, was the possibility of a code design to make sure that we can run, maintain the 1 to 2 milliseconds or close to it. You saw in that previous graph, I told you that 1 to 2 was without the process start. With the process start, we're looking at 5 to 6, but with Nanvix still we're under about 10 milliseconds, so we only added about 2 milliseconds of overhead. Because main use case of Hyperlight required that. Nanvix was looked pretty good for us, and it was one of the main things we considered for adopting it via the split OS design and so forth. You want to add, Pedro?
Yeah, I think that it's important that there is this tightly integration and co-design that is happening between Nanvix and Hyperlight, and it turns out that both are Microsoft softwares that we are growing internally. We don't have like an internal microkernel. Yeah. Besides Nanvix.
Have a question?
Yeah.
Currently, the cloud providers like Google Cloud supports gvisor and Kata Containers also. So, is there any possibility in the near future Hyperlight will be supported by default by any of these cloud vendors yet?
I would love to. Yeah, we're open source, so anyone can go in and grab Hyperlight and use it in any form. We're also part of the CNCF, which I guess makes that a little bit easier. We're governed by the CNCF, so Hyperlight is not owned by Microsoft in that sense. We're also looking for contributors. If people want to go in and contribute and then use it for their use case, that's all things that we're looking forward to have.
Great. Thank you so much.
Thank
It was
you.
a wonderful talk. So we'll break for 20 minutes. The next session in this room starts at 4. Thank you.